Today we're going to be talking about moments of force, another word for torque. So, torque is a turning effect caused by a force. It's going to cause something to turn or twist. Now, it can also be called moments of force or just moments. But remember, we've talked about moments of inertia, and they are different than moments of force or just moments, which gets really confusing. So we sometimes use the word torque and sometimes the moments. We have to be careful in not using the words moments of inertia. Now, what I want you to do is lay your notebook that you're currently writing in, or other textbook around you, or any book, it doesn't matter. Put it on the table, flat on the table. Now, find the center of it. Find the center of gravity. That's just easy. You just kind of find the crisscross and then find that line. Now, I want you to push just off to the side of that center point. Ever so slightly. Just give it a little push. Okay, what happened? Now, repeat that a number of times, striking the book a little bit outside of that line. So keep getting closer and closer to the edge and pushing, pushing, pushing. What happens? Well, you should see the book starting to twist, and the further out you are, the more it should have twisted. That's because the distance between the line of the action and the axis of rotation is going to affect how much it twists. So will the size of the force. If you pushed it a little bit, it shouldn't have done anything. Pushed it hard, and it should have twisted a lot. The turning effect is produced by a force and is equal to the product of the magnitude of that force and the distance of that force from the axis of rotation. So the distance between the line of action of its rotation is perpendicular to the distance between when the force was pushed. In other words, I'm pushing straight up. My distance is labeled here as r. So this is A is my middle point, my axis of rotation. So it is perpendicular going left and right while my force is going up and down in this picture. So mathematically, we can actually write this equation down. We can say that torque can be defined as tau is equal to, which is torque, that's a one-legged pie. So you can just basically draw pi with that squiggly top, and then you just do one leg rather than the two legs that you do with pi. And that is force times a distance. But Mr. Goddard, you said that force times distance is work. Yes, force times distance in the horizontal direction, when they're perpendicular to each, or parallel to each other, they are it is work. But force times distance in the perpendicular causes torque, and that's what this little upside down T says. This upside down T says it's perpendicular, so they have to be in the opposite direction. While F has to be in the X, R has to be in the Y, or vice versa. They cannot be in the same direction. So torque is measured in Newton meters or foot-pounds. Force is newtons or pounds. And the R, which is the distance, is always going to be meters or feet. Note, torque has direction and must specify that direction. So we say that if it's counterclockwise, it's positive. It's clockwise, it is a negative. This is important because we're going to have objects that are going to have positive and negative torques. And that's going to be important to denote which ones are positive, which ones are negative. So let's look at an example. The width of a door is 80 centimeters. If you open it by applying a 20 Newton force at 20 newtons at the edge away from the hinge, calculate the torque produced. Well, that becomes the length is 80 centimeters. But remember, we have to go to either meters or feet. So this is centimeters, so we're going to use the metric unit. So that's 0.8 meters. The force is 20 newtons, so we put that into our equation. Torque is force times the distance, so force of 20 times the 0.8, that gives me 16 Newton meters. I want you to do this one here, this example 2. In the previous question with the 80 centimeter door, if the handle of the door is situated 20 centimeters from the edge and the torque required to open the door is 16 Newton meters, what is the force applied through the handle to the open door? All right, so let's list what we know. First, the distance. It is not 20 centimeters. The handle is 20 centimeters away from the edge of the door. and the door is 80 centimeters, so that means it is actually 60 centimeters or 0.6 meters. Now, then we have a torque. It's given to us, our torque is 16 Newton meters, and we know that that's also force times the distance. So then we can plug in our equation. 16 newtons is equal to my force, which we're looking for, times 0.6. So I rearrange it, 16 divided by 0.6, which gives me a force of 26.7 newtons worth of force to push on it. Now, levers are going to deal with this torque because they spin, they twist. A lever is just a rigid object that is used with the axis to either multiply its mechanical force or effort or resistance force, the load. There are three components to a lever. There is the axis or the pivot or fulcrum. That's usually symbolized by the triangle. The resistance arm, which is where it's the load, it's where our load is located. And then the effort, where you are pushing, causing the effort to do something. Now, there are three different types of levers. There's a first-class lever, and a second-class lever, and a third-class lever. Draw these levers down so that you know them. Okay, first-class lever says that the fulcrum is fulcrum is in the middle. Your effort and your load are on the opposite sides of each other. Now, this fulcrum can move anywhere it needs to, but it has to be between the load and the effort. That's a first-class lever. Second-class lever, the fulcrum is at the edge, and the same with the third-class lever. The fulcrums are always on the edges. The difference here is that the effort is pulling up while load is down in the middle. Third-class lever is the effort is pulling up in the middle and the load is down at the end. Now, these two, first class and second class will always be easier to lift that load. This is a wheelbarrow where it's really easy because my load is in the middle, my wheel's here, and I'm picking up the lever. The second class or type 1 lever is a seesaw. This one's the hardest, third class lever. This is going to be your arm. If you put a weight in your end of your arm, like you're holding it with your fist, your elbow is the fulcrum, your effort is your muscles that are your bicep attached to your bone and pulling up. This is a third class lever. It's actually much more difficult to do this motion than it takes a lot more muscle than it would be if you were level 2 or level 1 object. So let's do an example. A uniform rod with a length of 50 centimeters is placed on a fulcrum in the middle, and a mass of 20 newtons should say weight of 0.2 newtons is placed at a distance of 40 centimeters from the left end of the rod. At what distance from the left end of the rod should a 0.6 Newton meter mass be hung? So, here's the important part. We are now a class 1 lever, and it's telling me these distances. Again, it's always measuring from one side to here, but let's go with this. We know that the clockwise and the counterclockwise has to be equal to each other, that the downward has to equal this, or it's not going to, it'll just not move. One side will start causing it to spin. So we know that the force on the times the distance on the left side, the right side, and the force times the distance on the left side have to equal. So now let's figure out our distances. Our forces on the right side is 0.2 newtons. The force on the left side is 0.6, which is easy. Those are the easy ones. The right side says that it is a uniform rod with a length of 50 centimeters is placed in the fulcrum. That means the fulcrum is located at 25 centimeters. And the 0.2 newtons is placed on the distance of 40 centimeters. So it's a little bit beyond that 25. And so we have to take into account of taking 40 minus the 25, which gives us the 15 centimeters. This is the important part, that the 15 centimeters came from the fulcrum to where that is. And this is why you have to draw the picture, because the distance is always from the point of rotation, the fulcrum, to where the force is located at, not from the edge. So we're always measuring from where the fulcrum is to here, and from the fulcrum to here, not anywhere else. So again, we're now trying to find what the radius of that left side is. So we plug in our equation. 0.2 times 0.15 is equal to 0.6 times the radius of the left side. We plug that in, and we get 5 centimeters from the fulcrum. Now that's not my answer, because again we're looking at from what is the distance from the left end. So we have to then, so the answer must be then 20 centimeters from the left edge. Again, 25 minus the 5 centimeters. This is important to draw it out. If you're still struggling with this, pause the video and draw it out and put the numbers next to it, and it will make a lot more sense. So let's look at some actual real life examples of different types of fulcrums. We have here is just our simple seesaw. A pair of scissors is like this. So we apply a force here. We have our fulcrum in the middle, and the scissors go chop. And that's our resistance. Our neck is a actual first-class lever. Second, which we already talked about, is where you have your fulcrum at the end and your resistance here, and your effort's pulling up. So your muscles are pulling up on your arm, and your resistance is, let's say, a weight in your hand. A wheelbarrow or your calf muscles are a second-class effort, where your calf is attached to your heel, pulling up, and your fulcrum is right at the ball of your foot, and your resistance is basically all the weight of your whole body being pushed down right through your leg bones. And so that's a second-class lever. As a muscle's attachments are much closer to the joint of axis, then the load of that muscle, the muscles have to create much larger forces in order to hold it a static position. So if you're holding a 40-pound dumbbell in your static position with your elbow at 90 degrees, the moment arm of your dumbbell is about 1.1 foot from your elbow joint. So what is that torque going to be? Well, again, torque is force times the distance of 1.1. So 40 times 1.1, or 44 foot-pounds of force. To hold that in equilibrium, your biceps must create a clockwise torque to equal the counterclockwise torque created by the dumbbell. So if the muscle attachment is only 2 inches from your joint, what force must the muscles keep kept in order kept the dumbbell from out of moving? So we then go in, and again we say it's 2 inches. So remember, 2 inches have to be turned into feet. So 2 divided by 12 is 0.17, and we say that 44 foot-pounds is my torque, has to counteract by some unknown force, which is what we're calculating, times the distance of that 2 inches, or 0.17 feet. I rearrange that. 44 pounds divided by 0.17 gives us 264 pounds. So in order to hold up a 40-pound dumbbell, your muscles actually have to support 264 pounds of literal force in order to hold it. So again, if you need to, the big thing here is to draw out the moments. Draw out the lever arms and figure out what's happening. If you have any questions, please write them down and ask me in class.